This talk is called How Big is the Universe? And attempts to answer one apparently very simple question. And it will take just over an hour, I think, to go through this and try and come to some sort of conclusions about it. Because as with all questions, it turns out to be more complicated than it first appears. So the first ideas about the universe really were the idea of all of the planets orbiting around with the Earth in the center, the geocentric model, and the planets, including the moon and the sun as planets. Anything that moved was a planet, and they all orbited round. And then you had the fixed stars in a sphere around the Earth, surrounding it, that carried them around their journey around the Earth every 24 hours or so. And this is all well and good as a theory of the universe, but of course it begs a very interesting question. And that's illustrated by this picture here, showing actually a flat Earth, but nevertheless with a hemisphere of stars above it, and all of the planets and the sun inside of that zone. And of course, we know that the Earth is not flat, and it is indeed talking about the Earth and the orbits. But the shepherd here is asking the question, what's outside the edge of the crystal spheres that carry the fixed stars? And he's poked his head through and can see all of the cogwheels up at the top left there, and the inner workings of the machinery that was assumed to perhaps drive everything around in the circles around the Earth. Now, what's behind that question is really another version of the same question, how big is the universe? And the shepherd here is worried about whether or not there is an edge. In other words, he's asking the question, is the universe infinite? And that's a very important question, and one that we still do not have a perfect answer to, but I'll try to convince you of what I think the answer is during the course of this talk. Now, the first person to really have a go at this was Olber, and he made perhaps the simplest observation of all time in astronomy, which is that at night it gets dark. We see lots of stars. Now, this may not sound particularly profound, but what he noted was there were not an infinite number of stars. There was a finite number of them with gaps between. And thinking about this, Olber reasoned that if you had an eternal and infinite universe containing an infinite number of stars dotted around roughly equally all over it, then eventually all lines of sight from your eyeball, no matter which direction you looked out into the universe, that line of sight would eventually land on the surface of one of the infinitely many stars. Might have to go a very long way, but ultimately there would always be at least one star on any line of sight if there were an infinite number of them. And if that were true, then all the lines of sight would gradually fill in to appear as bright as the surface of a star does, rather as illustrated in this animation here. As all of the stars are gradually taken account of, the more and more distant ones fill in all of the gaps to the point where there are no black areas left. And so the sky would not be dark at night, it would be fully bright. In fact, we would be toasted by the combined heat and light radiation from the whole sky looking as bright as the surface of the sun does, because all lines of sight would be equally coming from the surface of a star. And that's quite a profound observation. And it says that one of those things at the top there must be wrong. It's either not eternal, not infinite, or doesn't contain an infinite number of stars, or 2 out of 3, or all 3 of those could be true. But at least one of them must be true. Now, some people raise the objection saying, but sometimes the line of sight in particular directions is blocked. And in particular, we see these dark nebulae, like the Horsehead Nebula on the left there, blocking out the light from stars that are behind it. And so there would be lines of sight that correspond to no stars being visible. And then same on the right here, we've got Barnard's Nebula, which is a dark, dusty molecular cloud of gas. And you can see 1 or 2 bright stars peeping out of it, but in general, it's blocked the line of sight from the stars of the Milky Way behind it. That's fairly clear. Now, we know this cannot be right because gradually the starlight that is being blocked must be being absorbed by the blocking object. And if that were going on for long enough, then it would heat the object up to a really quite warm temperature. And we can measure the temperature of these clouds using our infrared telescopes, and indeed show that they are very cold indeed. And so they're not the solely responsible for blocking all of the infinite amount of starlight that would be coming from behind them in Olber's ideas. And so that man Kepler got in on the act and had to think about this question as well. And what he said was, perhaps it's infinitely large and infinitely old, but only contains a finite number of stars. In other words, implying that the stars thin out or stop at some point as you go further away. And that would be a sufficient explanation to explain Olber's paradox, that eventually your line of sight would go beyond the point where there were no more stars without having hit anything. You do need an infinite number of stars to fill in every possible line of sight after all. But it's not really what we see. This picture on the right here is taken by Hubble, and there's a couple of bright stars that are shown by the diffraction spikes. And I know David's on the line and doesn't like diffraction spikes, but the rest of the objects are galaxies, and there are thousands and thousands of them in the photograph. We'll talk more about that in a minute. But really, to get a grip on this question, we need to actually start measuring distances. The question then is, well, how do we know how far away the stars are? We can't exactly unfurl a cosmic tape measure and go and measure the distance. We need a very long tape measure and a rocket that could take us there and bring us back with the answer. And we just don't have that. So let's start a little bit less ambitiously. Rather than measuring the distance to the stars, let's just measure the distance to the sun. Well, it turns out that's quite difficult, but it was done by Aristarchus of Samos, a very clever method that he came up with. And he realized that if you looked at the moon when it was at exactly half phase, then the triangle made by the moon, sun and the earth must have a right angle at the point where the moon is. And so from his knowledge of trigonometry, he could measure the angle between the direction of line of sight to the center of the moon and to the sun. And if he could do that accurately enough, he could solve the shape of the triangle. And he measured it, and he reckoned it was 87 degrees, that angle, meaning that the angle at the sun was the other 3 degrees, and calculated, therefore, that the distance between the earth and the sun must be something like 18 to 20 times further than the distance from the earth to the moon. Well, that doesn't quite solve your problem, but you can use other events. You can use a solar eclipse, as shown on the right, where the moon goes directly in front of the sun, and yet that tells you that the ratio of their sizes is proportional to the ratio of the distance. It turns out by cosmic coincidence that the moon is 400 times smaller than the sun and 400 times nearer, and so it perfectly blots out the sun in the sky. And of course, we can measure what angle that is, and it's half a degree across the disk of either the sun or the moon. But you could also get a handle on this using the other type of eclipse illustrated in the bottom diagram, where the Earth goes between the moon and the sun, and the Earth's shadow covers the moon. By measuring the parameters of that, you can actually get enough information to solve the equations and work out estimates of the actual distances. And Aristarchus did all of that. He wasn't absolutely right. There were one or two things that tripped him up. The measurement of 87 degrees is not quite right, because the sun's rays coming in at a low angle through the atmosphere get refracted, and he didn't know about that. And so that would have changed his answer from 87 degrees to 89.5, and obviously make quite a big difference. But about 1,000 years later, people were still trying to actually get a grip on the size of the solar system, and they realized there was a method involving the planet Venus that could be used. If you observe Venus crossing in front of the sun, and there's a little picture that I took in 2004 when Venus passed in front of the sun, a little black dot there blotting out some of the sun's light. But if you observe that from different locations on the Earth, a known distance apart, then as shown in the bottom diagram, the dot of Venus moves across different chords of the disk of the sun, and they take different lengths of time as a result for the transit. So it depends where you are, and that allows you to use trigonometry to solve the size of the Earth's orbit, and indeed then the orbits of the other planets as well come from that. And so that was a very popular sport when the transit of Venus was happening in the 19th century. Okay, so if we now return to the distance to things outside the solar system, we can start to use trigonometry on them as well, if we can make very precise measurements. And the way we do it is we use the baseline now of the whole of the Earth's orbit. So for taking measurements at 2 points 6 months apart on the Earth's orbit, we get a baseline of a triangle that is 300 million kilometers across, 2 astronomical units. And if we note that a nearby star to the sun changes its position compared to the stars that are very, very far away and therefore don't appear to move, then we can get an estimate of the distance based on the trigonometry. And this is called the parallax method. You can do it yourself if you I usually get people to put their thumb up and stick their thumb out in front of their face and line it up, having shut one eye, with a distant object, and then switch eyes, and the distance between your eyes causes the nearby object to shift its position compared to the distant background, as shown in this diagram. And it's in that method that the human brain computes the distance to objects and allows you to do things like catch a tennis ball that's been thrown towards you, because you can see the change in the parallax as it's moving and work out the speed and distance of the object. And so for that, we can do that, but we can only really do it for the nearby stars where there is enough of a shift in the position. And initially from the ground, the limitation was the precision with which we could make those observations, and that's about half an arc second, because that's limited by the atmospheric turbulence in the Earth's atmosphere that causes stars to twinkle and so forth, causes about half an arc second of movement just because of the turbulence and blurring out effect on the stars themselves. So we can't be any more sure than that as to how what their position actually is. To get around that, you have to go to space, and one mission that did that very successfully was the Hipparcos satellite. And that measured angles to 1/1000th of an arc second, so 500 times improvement, and was therefore accurate out to about 500 light years, able to give us really quite a good map of the local part of our universe, of our Milky Way, with several hundred stars within that distance. Got a little diagram there of a few of the local ones. You've got the sun in the center, and if you look there, you can probably recognize some of the names like Arcturus, Sirius there, really quite close to the sun. That's why they're so bright. And as you go further away, we've got at the top there Castor, Aldebaran and Kepler showing up, and those are further away but a bit brighter because they're actually all giant stars these days, giving off a lot more light. Now, the next step really is to try and extrapolate from the known stars that we've measured using a method called standard candles. The illustration here is a series of candles of equal power output, but at different distances, and the further away ones look fainter in proportion to the distance that they are from the observer. In fact, related to the square of the distance. It's another of these inverse square laws. And so if you have an object twice as far away, it will appear a quarter as bright if the power output is the same, if it is a standard candle. And that turns out to be quite a useful method. So if we can look at stars and say, well, that star looks in all respects very similar in its color and its spectrum of its light to another star where we do know the distance, we can perhaps make an estimate of its distance just based on the relative brightness of the two. So now the story turns really to a couple of other very famous individuals. Immanuel Kant, the philosopher, in 1755 proposed that the stars that we saw were part of the Milky Way, and that this was a huge collection of stars whirling around, held together by their mutual gravity. And as shown in the picture, though that's a picture of the Andromeda galaxy, not of our own. We can't take a picture of our own because we are inside it. It's like trying to take a picture of your house and its garden by standing in the bathroom. We really got a very poor view of our own galaxy from where we are. So actually that's a very, very good inference. And of course he knew about Newton's laws of gravity from 50 years earlier and all of that. So he used that and just the power of his mind to really explain what was going on in terms of the stars and the Milky Way that we saw in the sky. 30 years later, William Herschel had a go and actually did the first map of the Milky Way galaxy. And this is it, this strange thing that looks like a sea monster here with all the dots and the tentacles is Herschel's map. And the bright object right in the center, let me get my mouse pointer here, that is us, with the sun positioned there. And what he did was he measured the brightness of many, many stars that he could see in the sky and their direction. He flattened their direction to a two-dimensional direction, not worrying about the up and down, but just the direction in the plane of the Milky Way, and plotted them on a clock face relative to the sun, with the distance out from the sun representing how bright they were, or in fact how faint they are. So he had the brightest ones plotted near the sun and the dimmer ones further away in proportion to their dimness. Now, the reason he did that was he said, well, I don't know that they're all standard candles and that they're all equal in power output, but I'm going to have to make that assumption because it's probably more true than not on the average, and it might tell me something. even if the detail is not entirely right, because some of the stars are more powerful than others. Now, the photograph up at the top there is one of the Milky Way, and I've oriented them the same way from the top left to the bottom right as Herschel's sea monster diagram, because you can see here these bright regions here with the dark dust lane between, that we now know is dust obscuring more distant stars, is mirrored in the structure that we have here. And the same sort of thing happens at the tail end over here with some of these dark dust lanes. And the overall shape is of a disk with a bulge. So he's not too far wrong with that. I think it's a very, very good attempt. Now, the debate about other objects that we saw with our telescopes that look like spiral clouds, spiral nebulae in space, went on for many years, with some people arguing that they were separate from the Milky Way and they were additional galaxies, additional island universes, as they were termed at the time during the debate, because the other side argued that the universe was the whole of the Milky Way, and that there were these clouds of spiral-looking gas were nothing more than whirlpools of gas in space inside our own Milky Way. And indeed, there was a great debate about it, the great debate in the 1920s, and this went on between Harlow Shapley on one side and Herbert Curtis on the other. Shapley argued that the Milky Way was the entire universe, and the spiral nebulae were just clouds of gas inside it. And Curtis argued that they were additional island universes, by which he means what we would now term separate galaxies, out in the universe. And they both argued with various different bits of evidence, but nobody had a particularly definitive answer. There was one that I think should have been a clue, and that was that there were more sudden brightenings, these novae where stars suddenly get brighter, in the Andromeda nebula, as it was then called, than there were observed in the whole of the Milky Way. And that should have indicated that it was, in fact, more on the Herbert Curtis island universe side of the argument. But there were lots of people arguing different points back and forth. Now, the resolution of this required an understanding of a standard candle, and that standard candle is a type of star called a Cepheid variable. These are named after the first star of the type to be noted, Delta Cephei, in the constellation of Cepheus the King. And these are rather unusual, massive, yellow giant stars, and they pulsate in brightness. And they do it in a very predictable way. Once we discovered enough similar examples, we realized that the pulsations have this sort of graft shape at the bottom here, where they go down relatively slowly and then climb quite quickly to a peak and then repeat. And the repeat period was directly proportional to the height of the peak. So those that had weak pulses pulsed very quickly, and those that had much greater swings in power output pulsate more slowly in an entirely regular manner. Now, this is very useful because it means if you measure the period of one of these stars, you can infer its power output, because we can easily measure the relative change in brightness as it pulsates. And if there is a linear factor relation between that and its power output, then we can just measure the pulsating interval and infer the actual power. And then using the idea of a standard candle, from that power output and how bright it appears to be, we can work out the distance. Of course, we need to know the distance to some Delta Cephei stars in the first place. And fortunately for us, there are some that were near enough and were within that 500 light years or so of our ability to measure. In fact, there were some that were nearer than that. A good example is Polaris, the pole star. That's a delta Cepheid, and it's a yellow giant star that pulsates like this. And so this whole idea enabled Edwin Hubble to settle the great debate, really. He measured the period of a variable star in the Andromeda nebula, as it was termed at the time. And his discovery photograph is on the right. It's in the negative. He's marked with N a few things that are novae, that were these exploding stars. But he's at the top crossed out N and written var, because the star got brighter and then dimmer in a regular pattern, just as it would if it was a delta Cepheid variable. And that meant he could work out the distance from its apparent brightness using the standard candle idea, and reason that this was 1 million light years away from us. Now, at the time, we estimated that perhaps the Milky Way was something like 50,000 light years. And so even if there's a little bit of error in the estimates, a distance of 1 million is so much further away. It's 20 times as far away from the Milky Way as the Milky Way was in size. So 20 galaxy sizes away. And that really told us that the universe was much bigger than anyone had previously estimated, and that these galaxies were separate island universes or galaxies in their own right. So here's a marvelous picture of the Andromeda galaxy. Around about 1 trillion stars in it, 220,000 light years in diameter, and 2.5 million light years away as measured by the most modern techniques. So Hubble was off by a factor of 2.5, but that was enough to settle the argument. And indeed, here's a little map of the local group of galaxies. We've got Milky Way top left and Andromeda bottom right. We also got the Triangulum galaxy, which is the 3rd largest member. And we're not sure if the Triangulum galaxy is in an orbit around Andromeda or minding its own business. We haven't been able to work that out. But both of them are coming towards the Milky Way. The whole lot are collapsing towards each other at 163 kilometers per second. But it's going to take about 4,500 million years for them to arrive and collide with the Milky Way and begin merging. We also got lots of small dwarf galaxies, as you can see there, some orbiting the Milky Way, some orbiting Andromeda, and one there, this one here, lost in space in between. And so that's our own local group, as we call it, and it's about 3 million light years across, and pretty much that's the whole contents of it. And then there's a void out beyond that to the next group of galaxies, which is around 10 million light years away. And so galaxies occur in clusters, and then the clusters cluster into superclusters. But the superclusters are then pretty much the largest structures in the universe. That's where the top of the structure tree maps out. And the large supercluster that we are a member of is in the direction of the Virgo constellation, and there are about 10,000 galaxies in it, and we are hurtling towards it at 2 million kilometers an hour, so a tremendous speed. But it's 50 million light years away to the center of the cluster, so it's going to take a very long time to get there. When we look with the digital sky survey by the Sloan telescope, we've actually mapped the structure of the universe and the structure of the galaxies, and they are shown in this image. Where there's the 2 missing pieces, those are the bits that hadn't been mapped at the time, so they're not voids, but the 2 slices of the circle there, the 2 sectors north and south, that have been mapped show every individual dot is a galaxy, and then they've used color to indicate where the density of galaxies has gone higher. And you can see the filamentary structure of the universe laid out here. The galaxies seem to form into knots, and the knots are connected by chains and filaments together. And we understand why that is now, we think, because our computer simulations come up with more or less that sort of structure. We think that all of what we know and what we can see at the moment in any detail is part of the Lanikailea supercluster. The little red dot is the little tiny obscure arm of this super filamentary structure, and then the dots are individual clusters of galaxies all hanging around on these immense and fantastically detailed filaments. It's an amazing view, and that's the map there of the largest piece of the universe that's ever been created. So not only did Hubble figure out that the separate galaxies were indeed separate and increase the apparent size of the known universe by a factor of 20, but he went on to measure the local galaxies are within a radius of our own, and measure the speed with which they were moving towards or away from us. So I said that the Andromeda galaxy and the Triangulum galaxy are coming towards us because gravity's got a good grip on them and is pulling them in. But he found that all of the other galaxies were all moving further away from us, and that the further away they already were, the faster they appeared to be moving, regardless of which direction you looked. And he produced this famous plot with the straight line there showing that the speed with which they were moving is proportional to the distance they are away. Now, this really only makes sense if you understand that the universe must be expanding in all directions. And if it's doing that, then it must have been smaller in the past. And so this then fed in as a strong piece of evidence towards the beginning of the universe being a hot, dense state from which everything expanded outwards. And we could indeed run the film backwards, if you like, to work out the age of the universe, the age since it was in a hot, dense state right at the beginning. And we get a figure now of about 13.8 billion years. So 13,000 million years, if you prefer. Now, this wasn't a surprise to a number of people. In particular, Georges Lemaitre, who was a Catholic priest and physics professor, because he had derived Hubble's law from Einstein's general theory of relativity 2 years earlier, and worked out that this is what you should observe in the universe, that you would in fact see a uniform expansion going on. So very great achievement by him. And he came up with the idea, therefore, that it must have been smaller in the past and had come from what he termed the primeval atom, this super dense state of all matter being confined to a very small region. Of course, now call that idea the Big Bang, and it's down to this man, Sir Fred Hoyle, based in Cambridge, and he didn't like it. In fact, he coined the term Big Bang as a term of derision, and it was first mentioned in this transmission in 1949 on the BBC Third programme. And I don't know whether you can read it, but it says, where it's highlighted, these theories were based on the hypothesis that all matter in the universe was created in one Big Bang at a particular time in the remote past. So that was the first use of the word Big Bang. It then goes on to say, it now turns out that in some respect or other, all such theories are in conflict with the observational requirements, and to a degree that can hardly be ignored. etc., etc. And he really was going on to poo-poo the idea of the Big Bang origin of the universe at all. Reason being, he had his own theory, which was the steady state model. What he said was, yes, the galaxies are moving apart from each other. He couldn't deny that from the observations. But he said that what happened was that more matter was then created in the voids between them and then got together and formed new galaxies. And so if you took a snapshot of what the universe looked like now, and you came back in a few billion years' time and took another snapshot, it would look almost the same. The pre-existing galaxies would have drifted apart and new ones would have formed in the gaps, keeping the average density of galaxies steady, at a steady state, a steady average overall density of the universe. And also, this implied that the universe would be infinitely old and that it would always look now and always look as it does now in the distant past. Now, of course, we could check that, because when we look out into the universe, here's that picture again with the many, many galaxies and the one pointy star there. We look into what is apparently blank piece of sky and it do a long enough exposure, and this is the Hubble Ultra Deep Field. They pointed the Hubble Space Telescope at a previously thought to be blank piece of the sky on the sky map and exposed a 1 month long exposure and produced this photograph. And it shows galaxy after galaxy, and some of them look like they're 12 billion years old, and that the light has been traveling that length of time across the universe to get to us. Now, if this particular area of the sky is typical of the rest of the sky, which we haven't checked because telescope time is very expensive and a month is a very large bill for use of the telescope, but we would estimate that if this density were roughly the same in every direction, that there would be 100 billion galaxies scattered across the sky out to that distance that we've been able to observe. But when we look at this photograph, we notice straight away that the distant galaxies look different to the more nearby, easily recognizable ones. They're actually different shapes. They're a little bit more irregular and less well defined. And of course, they're also very red in color. If you see a red object in here, like this little red dot here, that is a very distant galaxy, and perhaps another not quite so distant one there. And that's because the light coming from those galaxies is traveling through space that is expanding, and as it does so, it gets its wavelength stretched, and it's the further away it has therefore come from, the more stretching that light has had, and so the more it is shifted into the red end of the spectrum, the longer wavelength end. We call that the red shift. And of course, when we're looking at these very distant galaxies, we're not only looking a long way in space, we're looking back in time and seeing them as they were, not as they might be today, because of that speed of light and the distance and how long it's taken the light to get to us. It's quite awe-inspiring to think that we are imaging objects that are where the light has been traveling 12 billion years to get to us, and that they're that far into the past. Now, just as an aside, I've got the notes on how we know that the speed of light is not infinite, and the first person to have a go at this was Galileo. He used a lamp and he got his assistant onto a distant hilltop with another lamp and tried to do an experiment whereby he would expose his lamp, and when the assistant saw the light, he would uncover his. Galileo would then see his assistant's light and cover his own back up, and so it would ping pong backwards and forwards between them, this lighting and unlighting, and he'd be able to use the round trip delay to work out the speed of light. Now, of course, it doesn't work very well because with the assistant only about a mile away, the round trip time is so short that human reaction times ruin the experiment. But he did at least conclude that it was at least 10 times faster than the speed of sound. And Ole Rømer then came along and had a go at this, did the same experiment using the moons of Jupiter as his assistant, and the fact that they disappear behind Jupiter was the equivalent of Galileo's assistant covering them up and then revealing them when they came out of eclipse. And by doing that and using the geometry shown on the right here, looking at the events and timing when they occurred with the Earth at different positions around the Earth's orbit at points G and F, for example, he could work out that the eclipse appeared to happen later than predicted at point F than at point G by the travel time of light from G to F. And so he got quite a good figure as shown at the bottom there. And of course, we've made much more precise measurements of the speed of light since, with devices called interferometers. This is Michelson and Morley's interferometer. It measures the speed of light very, very accurately. In fact, what they were trying to do was determine if the speed of light was moving, some influence moving through a thing called the ether, and see if there was an ether wind that the speed of which could be measured blowing across the Earth as the Earth moved around the sun, and it would change its relative direction towards any ether wind. And they found absolutely nothing. The speed of light was completely constant. But of course, this was explained by Einstein in 1905 with his theory of special relativity, which tells us that the only fixed thing about observations is that the speed of light is the same no matter what observation you make or how the observer is moving. And so, going back to the Hubble deep structure and Hoyle and his steady state theory, turns out that what we're observing way back in the past, using the speed of light to determine how far away and therefore how old these objects are, does not look the same as the modern universe. The big thing to note really is that the ancient universe contains many quasars, which are the early forming galaxies, where there's a black hole, a supermassive black hole forming in the middle of the young and chaotic galaxy, and feeding voraciously on infalling material, and that creates a very powerful jets of waste material shot out from above the poles along the magnetic axis, and creates these very bright objects called quasars. And we don't see them anywhere nearby in the modern universe. And so I'm afraid, Fred, wrong. The universe does not look now as it always has done. It has changed, and changed quite considerably. Well, so we now have the modern theory of the Big Bang, and it's summed up in the diagram on the right here, with the Big Bang happening. We don't know what triggered the Big Bang, but it happened, and through huge amounts of energy into the universe, there was a very rapid period of expansion, and then things settled down a bit, and eventually the stars and galaxies started to form about 400 million years after the Big Bang had occurred, when things had begun to calm down a bit. But the piece shown here, if you see my mouse pointer, this pattern here, this is the afterglow light of the Big Bang, and dates from just 380,000 years after the Big Bang. And that was discovered by these two gentlemen, Penzias and Wilson in 1964. They were actually telecoms engineers, and they were trying to produce long-range communications and were having trouble with a persistent noise that seemed to fill the sky no matter what direction they were looking. Everything they did were trying to debug their equipment. They even had their student engineers climb inside the giant horn antenna and evict the pigeons and clean out all the pigeon muck in case that was the source of this background noise that they just couldn't get rid of. But eventually they were put in touch with some theorists who had predicted that there would be this leftover heat signature filling the sky if the Big Bang theory was true. And so they shared the Nobel Prize for the discovery of what we now call the cosmic microwave background radiation, this pattern of heat that is the afterglow from the early time in the universe when it was very hot and dense. When it was emitted, it would have been 3,000 or 4,000 degrees Kelvin, the temperature of a red star, and the whole universe would have looked a little bit like a red giant star, I suppose. But the time since and the expansion of the universe since has cooled that radiation by a factor of around 1,000 or 2,000 from its original wavelength, stretching it out and making it so that the wavelengths are no longer in the red part of the visible spectrum, but are down in the microwaves region and with a equivalent temperature of just 2.7 degrees Kelvin. So we have this Big Bang and we have the universe expanding. So we can start to ask some new questions. Where is it going in the future? We know that gravity is pulling everything towards everything else. And so perhaps there is enough gravity to gather the material back together, reverse the expansion, and lead to a future big crunch. And that would be shown as this trajectory for the universe, starting at zero size here, coming up to now, and then continuing to expand, but at an ever decreasing rate until falling back at some distant point in the future to the big crunch. But on the other hand, if there's not enough gravity, then maybe the universe has got essentially escape velocity already and got enough energy of expansion to overcome that gravity and to run away and escape forever. And it could do so on one of these other trajectories like this. It would be rather nice to know. Now, another piece that we have only briefly touched on in this was the discovery of dark matter. And this is Fritz Zwicky, who estimated that the mass of all of the galaxies in the photograph here, the Coma cluster, was not enough. If we added up all of the equivalent brightness of the stars, we could estimate how many stars there were. And again, in the same sort of way, say, well, on average, the mass of a star is whatever it is. And so estimate the total mass of the galaxies and therefore their effective cluster gravity. And then looking at the redshifts and the Doppler shift of their movement, we could work out their speeds. And he worked out that their speeds were about 10 times too fast to keep the cluster bound together. It should fly apart, but clearly it hadn't. And so something must be pulling that material together much more strongly than we could account for. And he came up with the idea that it was perhaps dark matter that was responsible for that. And maybe that will influence the overall outcome of the universe going forward. So those are quite a number of aspects of our sort of modern theory of the Big Bang, the composition of the universe, the expansion of the universe, the amount of matter that's in it, and so on. But it still leaves quite a number of questions. And so what I'm now going to do is go through the questions that I'm always asked after I've talked about the Big Bang. And I've entitled the next slide, tricky questions. And so the first one is, what came before the Big Bang? The next one that people ask me is, where was the center of the Big Bang? And perhaps the most popular of all, if the universe is expanding, what is it expanding into? And another one related to relativity is the expansion moving things away from us faster than the speed of light? And these are all excellent questions that show that people have really been listening and understanding what's been said, because these questions are all hiding there, waiting to be attempted. So let's have a go with what I call tricky answers. So what came before the Big Bang? Well, my tricky answer to this one is that time itself was created at the Big Bang along with space and energy. And so without time, there could be no before. There is no sense in which there was an earlier time. And in the same way, you can imagine traveling on the Earth and trying to go north. And eventually you come to the North Pole. And you can't go any more north than the North Pole, because that's where the coordinate system has its origin. It comes from there. And so is the case with time. It emerged from the Big Bang and expanded outwards along with space in every direction. But there was no going before time zero. It's like trying to go further north than the North Pole. Where was the center of the Big Bang? And this is because everybody is told by the media that this picture that I've shared here represents the Big Bang of an explosion outwards from a center. It's a concept we're very familiar with in the everyday world, of things exploding like that. But the answer is the Big Bang was not an explosion of matter and energy outwards across space. It was actually an exponentially rapid expansion of space itself. And so it is not that things were thrown outwards across space from an origin, but that all the places in space were initially together, and then somehow suddenly they expanded outwards, and every gap between every object, between every point, had more space created in the gap. And so actually the answer is that everywhere was the center, and everywhere is equal, and there was no center to the Big Bang. Copernicus would like this. You know, we are not the center of the universe. At least we have no greater claim to be the one fixed reference point than anybody else, it turns out. So that picture is wrong, and you have to work quite hard to get that out of your mind when thinking about this. In an expanding universe, we can think of it as shown in this diagram on the right. All the galaxies are receding from you, and nobody is special, and you are not the center, and nor is anybody else. So let's pick this purple galaxy. Let's say that's us. And if you look around us here, you see that we have a group of galaxies, all roughly 1 grid square away. After a certain length of time, the grid squares have got bigger because the universe expanded, but nobody's changed their position on the grid. It's just the grid's got bigger. So they've not moved through space, but space has grown. And the relative positions have been preserved. But what's interesting is that if we say decide to be this blue galaxy instead, we can say exactly the same thing. All of the neighboring galaxies have moved away from us by the same amount. But if you look from the blue galaxy to the black one here, let's say that's 1 unit, and over to the green one is 2, after a certain time, the distance to the black galaxy here has grown. Let's say that's 1.5 units now. And the distance to the green galaxy has gone up to 3. And so that is Hubble's law, that the one that was further away has gone from 2 to 3. So its recession velocity in 1 unit of time is 1, 3 minus 2, whereas the black galaxy, starting nearer, has gone from 1 to 1.5. So its velocity away from us is less in direct proportion. So that's really the explanation of the whole idea of the expansion of the universe. Okay, and nobody being the center. There is no center. And of course, what we're doing is representing the whole of the universe as the two-dimensional surface of these three-dimensional balloons that we're blowing up. But we're not saying anything about the contents or the volume of those balloons. We're pretending that the 3 dimensions are all encompassed in the 2 that are the surface of the balloon. We have to do that because our brains are not very good at thinking in 4D, and it's certainly not very easy to show it on a PowerPoint presentation. So the next tricky question was, if the universe is expanding, what is it expanding into? And so to answer this one, I repeat that the Big Bang was not an explosion, and that space itself is the thing that's doing the expanding. It's not expanding into anything. The space gets bigger, but it's not a question of moving from the space you were in into some new region. Okay, and I think you can see that if you think about that balloon diagram again, at least I hope you can. So then we have this question: is the expansion moving things away from us faster than the speed of light? And the answer to that one, surprisingly, is yes. But it's the expansion of the universe, is because it's not movement of galaxies through space, it's the expansion of space. That's okay, because it's only movement through space that is limited by relativity to not be faster than the speed of light in a vacuum. Okay, movement through space must be slower or equal to the speed of light, but space itself can expand at any speed, including speeds faster than light. So that's not a problem at all. Now, here we're going to try and get to the answer of the question that I came up with: is the universe infinite? And because the speed of light is finite, we know that, we've measured it very precisely, and we know that the universe is finitely old. The Big Bang happened 13.8 billion years ago. There is a distance beyond which you cannot see, your cosmic horizon. This is places in the universe where the light has not had time yet to reach you, given its distance and the distance of the amount of space that it has to cross to get to you. So this cosmic horizon grows with time. Every nanosecond, the cosmic horizon gets 1 foot larger, because light travels 1 foot in 1 nanosecond. 30 centimeters in a nanosecond is a light foot. It's how far light will travel in 1 billionth of a second. It's quite a useful figure to remember sometimes. And so as the universe gets older and older, the light has had more and more time to do the traveling, and so the horizon around us appears to enlarge. Or it would do if it were not for the expansion factor of the universe, because as the universe is expanding, it is making the apparent distance that the light has to cross be larger. And I say apparent distance, and I've been very careful with my words, because although the universe is only 13.7 or 13.8 billion years old, the distance to that cosmic horizon now works out to be 45 billion light years. You'd think it would be 13.7 or 13.8, wouldn't you? But it's more than that. And that is because the light beam set off from whatever object we're observing, went through some of the space, and then after it had gone through, the space expanded behind it. So it didn't cost the light beam as much time to cross that space as the size of the space became afterwards. And so if you work all of that out and you do the rather complicated calculation, you can work out that the oldest bits of space that it traversed first have stretched by an enormous factor, but the more recent bits that it's only recently traversed have hardly expanded at all while it was doing it, and it comes out to this expansion of the time from 13.7 to 45 light years. But whatever that number, it's very interesting because there could be objects beyond our horizon. In fact, I think there must be objects beyond our horizon, and I'm going to try and persuade you why. And the reason is that everybody has a different view of the cosmic horizon. Here's us here on Earth, and there's a theoretical planet out here at point A, right on the edge of our cosmic horizon today, just about come into view recently, and another one at point B over here. So we can see A and we can see B because they're just inside our cosmic horizon. But an observer on the planet at B has a cosmic horizon that just about reaches the Earth and goes like this. And he can't see A, and likewise A can't see B. And so for an observer at B, A is outside his cosmic horizon. Again, unless you're going to try and argue that Earth is special and right at the centre of the universe, at which point Copernicus will spin in his grave, then you must accept that our view is probably not special, and that therefore there will be objects beyond our cosmic light horizon. And so for many observers across the universe, effectively they would all have these cosmic bubbles that they live in, that they can see, and that those are expanding in apparent size, but the problem is that the farther reaches of those are beginning to race away due to cosmic expansion faster than the speed of light. And so there's a race between being able to see things at some distant point in the future when the light beam finally arrives versus them having been carried away and ending up beyond our cosmic horizon forever. Well, that's all well and good. Can we prove it? Well, there is some evidence of a thing called dark flow, and this is a very intriguing possibility that, observed from the Earth, when we map the apparent movement of all of the galaxies that we see in the universe around us, it appears that things are a bit lopsided, and in particular, some objects here on this side of the universe within our cosmic bubble are moving all out towards some point beyond the cosmic horizon that we can't see, as if they're being pulled by gravity. And so it's suggestive of the fact that there is a very large concentration of mass here out beyond the horizon that these galaxies are being pulled towards due to the influence of gravity that they are able to detect. It's within their cosmic horizon, but not within ours. And some evidence for this, and it's called dark flow. I'm not entirely sure if this is right. It's a little bit speculative. So we set out to answer the question, what is the size of the universe? And we haven't really answered it, but I'm going to argue that we've learned that it's a finite age, and the modern figure is 13.74 billion years, to give it to 4 significant figures, but that it's larger than we can see. It goes out beyond our cosmic horizon, and there are logical reasons for thinking that that is the case, as well as the possible dark flow evidence. But I'm going to suggest that it's probably infinitely large. And my reason for that goes back to the idea of this, in that you can extend this diagram with as many people on as many hypothetical planets to the left and to the right. And if nobody is allowed to claim that they are at the center, then there is only one answer for the size, because the only number that you can divide by 2 and still end up with you having the same number is infinity. It's as if there are an infinite number of these overlapping cosmic spheres of time around everybody, and that nobody's got a right to claim that theirs is the center. And if nobody's at the center, then there can be no edge, logically. And so I think the universe is infinitely large, but sadly, most of that, indeed an infinite amount of it, leaving an infinitesimal amount of it inside our cosmic sphere of observability, we'll never be able to see. I was going to say, we've got the Gaia satellite up there mapping the galaxy to even greater accuracy at the moment and producing great results. It's vastly improving on any map that we've had before, but it's still only looking at 1% of the stars in our galaxy. And the other thing that we haven't mentioned is the whole idea of dark energy and the observations that, based on using white dwarf stars as standard candles, the expansion of the universe is somehow speeding up, caused by some sort of anti-gravity property. And we call that dark energy. And that will be the subject of another talk that I'm going to do called Cosmic Dawn and Destiny, where I'll deal with the whole idea of the details of what happened at the Big Bang itself, as far as we know, and what we think about this dark energy and what's going to happen to the universe in the very, very long term, and the evidence for and against dark energy.